Hopefully it gets connected real quick. Yes. So currently we are streaming. Now, wait, has it connected? No, it hasn't. Oh, wait. Yeah, it's ready. Okay. So today our main focus would be to understand how different sorting algorithms change over different inputs. Okay. So in the last class, we basically have gone through how different algorithms uh, are working. Okay. Basically, we have gone through the algorithms each and every step. Now, in today's class, we will see the implementation of each of those algorithms. But not only that, we will also see how, as the input size grows, how those algorithms behave. And one of the important parts is when to use which algorithm. That means, say you have a particular work criteria, and in that particular criteria, you want to, like, you already know the input size. Okay. So, because you already know the input size, you can choose which algorithm you would be using for your own particular case. So hopefully that is understandable. Now, I would like to go through that animation as well real quick. Just a second. I think, do you have the website? Sorting algorithm website visualizer. Yes, I think this was the one. Oh, let's see. Okay, so this is a different one. Not that, because I want to see the step by step, not probably this one. This is a cool one, I would say. I think this was the one we followed. Yes, this is the one we were following. Okay. So you will see that my screen is split. Should I increase the fonts? Is it visible to you guys? I think this should be okay. Now, first we can go over the basics real quick again, which is what is sorting. Sorting is basically the process in which we are ordering an array of integers or numerical values which are quantifiable. Means there is some order between the numbers or maybe even alphabets. Understand that even alphabets have a alphabetical order. Okay. Even there is a good question that sometimes asked in the uh, interviews, okay, that can you apply the sorting algorithm over special characters? What would be your answer? Yes, correct. According to the ASCII value, if we are provided the ASCII like encoding, then of course we can apply the sorting algorithm. Okay, that's correct. Now there is one more thing. Okay, can we apply the sorting algorithm over emojis? Is it possible? Guys, can you answer? According to
UTF.
UTF. Okay. So I have a question for you right now. Is UTF enumerate? Means, is there enumeration in the UTF format? If it is enumerate, then can you tell me what is the like other operations? What are the other operations that you can perform over the emojis, or let's say other UTF encoded characters? Hmm? Okay, no issues. So your answer is correct that UTF characters means even you can apply sorting to emojis. Okay, or any of those UTF-8, UTF-16 characters. Now coming to my next question, where I asked that what are other operations that you can apply? The interesting thing is that you can apply any mathematical operation over those characters, because at the end of the day, those are what? Those are just hexadecimal string of characters, right? And here where I would like to give you one homework, or I think I gave you one earlier time as well, which is to not only go through the UTF characters, but also try to apply XOR gate operation, NOR gate operation, and other operations, okay, over the character strings. And you are going to basically, after you do the operation, basically convert it back to a UTF character and print it, okay. And telling you that you are going to find very, very weird relations between the characters, UTF characters, okay. So I would recommend you to go and do that, okay. So can you take it as a small homework? चलेगा? होगा होगा। अरे हाँ ना तो बोल दो। अरे हाँ ना तो बोल दो भाई। चलो ठीक है। अब क्या ही करूँ, कुछ हाँ ना नहीं बोलते हैं ये लोग। चलो ठीक है। Now let's continue. We have different types of sorting algorithm. One would be the comparison based sorting and one would be the non-comparison based sorting. What do I mean by comparison? That means there is an order possible, or there is this greater than, equal to, or inequality, or any of those three operations. Greater than, equal to, sorry, greater than or less than or equality. These three operations are comparison operators because they are like quantifiable units. Okay. So that's why these operations, when applied to a set of, let's say, strings, integers, or any other thing, they give you quantifiable comparison based approach. That's why they are called comparison based algorithms. There is another form of sorting algorithm which are sometimes better than comparison based because they are based on counting or radix or basically bucket sorting. These are the name of the algorithm, but they don't actually do the comparison. Okay. Means in those approaches, you won't find this, is this element, let's say ith element, greater than, equal to, or jth element, or is this ith element greater than, equal to the first element. Okay, you won't find this kind of lines in the algorithm itself. That's why these are called non-comparison based algorithms. Okay, now you need to understand that there are a few key metrics that we use, and the so non-comparison because they don't use that greater than, equal to, or sorry, greater than or less than or equality comparisons, okay, between two numbers. Bubble sort checks it. That's why it is under the comparison based. But there are algorithms which we will discuss today even itself, like counting algorithm, radix sort algorithm, bucket sort algorithm. Yeah, these are the examples. Can you see? Let me zoom in. Counting, radix. Okay. Yeah, I'm coming. So don't worry. Like in today's class itself, as we go along, you will be getting the examples. Okay. Fine. Just wait and you will see. Okay. Next we have the key metrics that we will be using: time complexity, space complexity, stability, and in place. Okay. So in place is a different metric. Not going to discuss much about it in this particular class. You know the time complexity. Can you explain the time complexity in just, let's say, one sentence, real quick? Anyone? जरा नहीं बोल रहा हूँ, बोल दो. Very good. Logarithmic scale, or let's say quadratic scale, that is a quantified approach. Okay, basically means how your algorithm performs as the input size grows. Okay, that is a मतलब क्या बोल बहुत ही simple definition of big O notation. There are better definitions which not required at your level, but understand what you like. What you said is absolutely correct, and that is the most important thing to you if you want to approach it in form of an engineer. Okay, but a more research oriented approach would be a little bit different. Okay, but yeah, Other than that, the space complexity basically means as your input size grows, how much additional memory you are required. Now, stability basically means that say there are equal elements in your whole array. So how do they maintain their relative order? Means if they are equal elements, are they always side by side, or are they actually at their actual position? So if they are in their actual position, so this is the in place, which basically means that it uses the constant extra space. When so a good example would be you have a fixed length array. Okay, because you have a fixed length array and you want to increase the size of the array because you have more inputs. Now, because you have more inputs, you need to increase the size of the array. So you are basically creating more space. Okay. Now, how this constant extra space, okay, is being utilized is giving you a new metric which is called in place. We will see it in action, but not that much. Now, understand that what Niket said about big O notation, that there are constant time, logarithmic time, linear arithmetic time, quadratic time. There is also something like the what is called this cubic time, quintic time. Okay, which
ব্যাপারটা কি বলতো?
n log n. So what do you mean is linear means it is n. Arithmetic, basically it should be linear and logarithmic. It's a combination of linear and logarithmic, but you will see that how the okay, let me show you how the n log n graph looks
গ্রাফটা
like.
দেখাও না, ডেসমাস করে।
Yeah, I'm showing you. So let's go and see images. Yeah, this is a good image. Wow, it's taking too long to open. Sorry. Wait. Image. Oh, this is here. Okay, see. What do we have? This is exponential. Sorry, this is exponential. This is factorial. Okay. Yeah, it is n factorial, which is matlab, very bad, very bad optimized. Okay, you should not be even thinking of having or using an algorithm which is having this kind of scaling. But there are algorithms, basically encryption algorithms, which if your input size grows, it takes that much amount of time to break it. Okay. Now, generally, most of the encryption algorithms are in the scale of somewhere n factorial or 2 to the power n or e to the power n or something like that. Now, this is n to the power 2, which is basically a quadratic algorithm. Now, you need to understand that where this is the constant time. Okay. This is the constant time, which is basically here. Okay. Now, after that, you comes the logarithmic. I don't know if you can see the logarithmic scale. Can you see this small strip? No. The say big O of 1. Big O of 1 is basically यहाँ पे in this representation they have put it directly over the x-axis. Okay. Say it takes zero amount of time. So imagine it like that. Okay. Fine. Now after that comes the log n. You know what happens in log n? It saturates. It saturates at some point. After that, basically comes the linear. It's a linear growth scale. Okay, it's a straight line. No. Think about it. So what is the log of 10,000? 3. Yeah, 4 log 10. Okay, say this is log base e. Say this is log base e or log base 10, whatever it is. Now, what is the O of 10,000? 10,000 is linear, right? So basically, 10,000 number, if I go from 10,000 to 1 lakh, it will go 10,000 to 1 lakh. But say in the logarithmic scale, if I go from 10,000 to 1 lakh, it will basically just be what? 5 log 10? Okay.
5 log
Right.
10, 5 log 10.
I'm not keeping the base. I'm keeping the base as whatever you want. So if it is 10, then you know there won't be anything. So that's there. But yeah, that's how basically you can understand that the growth rate of log n is smaller than O of n. You can just differentiate to understand it as well. Okay.
ঠিক।
Now, after that, you basically mix it up. So you take n times log n. So it's a mixture of log n and linear. So that's where it is standing. Okay. This means this is better than n square, but it is not as good as the linear, or even not as good as the. If it is not as good as linear, it is never be as good as log n. Okay, that is understandable. Now we know the bubble sort algorithm. So basically, how it works? It basically keeps like a bubble. Okay, like imagine that like that's a safe space for just two-person, and inside that bubble, it basically compares the two people, and there is a particular order. Okay, so in that particular order, if let's say you are arranging it from ascending order or descending order, you will always compare that if the next person is greater than or less than the first person. Okay, and basically you then move the bubble again and again and do it till you do not need to swap. Swap will only happen then when your predetermined order is not being maintained. Okay, so if the predetermined order is being maintained throughout the whole array, then that means you do not need to sort anymore. And this particular bubble sort algorithm we have seen in the previous class as well. Let's see the animation. Okay, this is the bubble sort. Let's sort it. So you can see it basically compares between two-person, and whenever it finds okay something is wrong, these people needs to be swapped, it will swap. Okay, so in the first run it swapped some number of times. Okay, in the second run it will again swap some number of times if required. Okay, as you can see the array is still not yet sorted, so it will keep on the sorting algorithm till it is able to find that no more sorting is required in the whole array. So as Dutika has already shown in her the demonstration that she has already completed the algorithm. This is again that algorithm itself what she has wrote, but a little bit with more comments and everything. And of course, I'm giving the test array inside this so that let's make it simple. So now within that time, you can see the bubble sort algorithm visualization has already completed. Understand that this website that you are seeing is implementing this whole approach, or you can say this whole algorithm in JavaScript. Okay, just a small take I would like to have on JavaScript. JavaScript is actually not a programming language, but what happened is that over the time people implemented so many advancements into the language that it's somewhere, I don't know, I can call JavaScript a programming language here, but it has evolved to almost like a programming language. Why I'm saying that? Initially, JavaScript had no code for it to maintain different memories, different processes, different. It never even had the logic to do this kind of complex arithmetic, floating point operation, and all this. Okay, but over time, what people did, they started evolving the language itself. Okay, so at this point, even though JavaScript still lacks a lot of the core programming uh, approaches, or let's say programming criterias, but over time it's almost becoming a programming language. Okay, so if someone asks you that what is the difference between Java or JavaScript or something like is JavaScript a programming language, at this point I would say it's somewhere in the middle. I would still not call it a true programming language because it's still lacking a lot of the core implementations of memories. But again, it is having that logic of handling different numbers. Okay, so I just wanted to have a small take on it. Nothing big, but that's it. If anyone asks you in, let's say, interviews or anything, probably my answer might not be the best. I would like you guys to have your own opinion on languages, because after a certain while, there is an ending of learning how much a language has already been developed. at that point you can even start contributing to that language itself. That means you yourself will be evolving that language, which a lot of people are actually doing. That's why I want you guys to later contribute towards the development of programming languages as well. Okay, बहुत ज़्यादा बात का बात हो गया. Let's continue with the selection sort. Okay, so in the previous class again we have gone through the algorithm of the selection sort. Okay, which is find a minimum element in the unsorted array. And you know how we find a minimum in the first case. We just assume that the first element we target is the minimum element in the array. Okay, and because of that assumption we then continue the comparing, and we just continue till we find the next minimum and then swap it with the first unsorted element, and we just basically repeat this process finding the minimum. By the way, you can do one more thing. You can actually look for the maximum as well. Okay, so it's not always necessary to always look for the minimum. Got it? Now let me show you the animation for the selection sort as well. So as you can see how it is working, it is assuming that the first element is the minimum, then it is looking for the next minimum in the whole array. And currently, because of some luck, we got the first minimum in the first case itself, so we don't need to look for the next minimum. But then it assumes that the what is the next minimum. Okay, then it again goes through the whole algorithm to find the next minimum. Okay, so we can wait just a few seconds. In the meantime, let me also run this Python code. Do you guys already shown? So I'm not going into the depth of how it works. So it will be said, don't worry. Next is insertion sort. Okay. At the last class, did we go through the insertion sort? I forgot about it. Can someone just remind me? Did we go through insertion sort? Or should we go through the algorithm of it? What do you guys want? Quickly. Yes, no, क्या? बोलो. अरे Dutika, तुम ही बोल दो. Should we go through the whole algorithm or we can just overview it?
I don't know.
Okay. Like I believe that I believe you are smart enough to go through the whole algorithm. We can just understand the main crux of the algorithm. Okay. So what we do, we basically consider that the whole array is already like not the whole array. Sorry, the first element of the whole array is already sorted. Okay, so then we pick out the next element and we see that, okay, which is the next element that should be there in a sorted array. That means the next greater element or the next smaller element, depending if you are sorting it like in ascending order or descending order. And you basically take that algorithm and drag it to the first and basically insert it. Okay, that's how you do it. Let's see a beautiful animation to understand it. Say here, we assume that this is being the first element and it has already been sorted. Then we drag the next element and we put it in the front based on the logic that is in the ascending order or in the descending order. So see, in the 7, it will now go back and look where we could insert the 7. That means where 7 is the next greater element of the last elements. Okay. See, it is now looking for 22. So then it is comparing that is 22 is smaller than which element, or 22 is last greater than which element. Okay, you could implement in both ways, it's up to you. Now for the 7, it is checking which element it is actually smaller than or greater than. Okay, because it was able to check through all the elements. Now you will see that the animation has ended and everything. Here, this is the insertion sort demo. Why?
তো মাইক্রোফোনের পাশে একটা পাখার লোগো দিয়ে লাল ডট দিয়ে
আমার মাইক্রোফোনের পাশে পাখা ও আচ্ছা this thing this is OBS. Okay, this is OBS. This particular software is responsible for this whole streaming. Okay. Okay, so if you want, you can also install it on your system and do streaming of your videos as well. Okay. Like you can also basically stream yourself doing some programming, doing some reading, explain physics or chemistry things, whatever you want to explain or
হ্যাঁ, তুমি অ্যাকচুয়ালি বলতে পারো স্টাডি উইথ মি ব্লগস করে দেখি ওরকম বানানো যায়, কিন্তু কি হবে।
okay.
তুমি বানাও স্যার, তুমি বানাও ডে ইন লাইফ অফ অ্যান আইজার কলকাতা স্টুডেন্ট।
I I don't know, I find that a little bit cringy.
নাইট লাইফ কি করে হয় সব তো ভরে গেছে ইউটিউবে, তুমি সব ভরে ভরে পাবে।
Like already people are making, so I'm like I'm just one another guy who will be making it. Okay, so forget it. Then it's the merge sort. Okay, so let me show you the merge sort. It basically breaks down. Okay, wait, let me show it by show depth. Okay, so it will basically split the whole array in between like two different parts. It will keep on splitting, and in the last splitted end where there are just two elements, it will then rearrange, and then it will go back to the like previous step and then again rearrange. It will again go back to the previous step and then rearrange. Okay, so basically divide and conquer. Oh, by the way, till now I was not actually going through the big O notation of each of these algorithms. So let me just quickly go through that while the merge sort animation is still playing. So the bubble sort algorithm had a time complexity of quadratic, which is the average one. Okay. And the space complexity of, okay, it should not be big O notation. It should be in sigma, but sometimes you can use big O notation.
এটা
Space complexity means as the input size grows, how much of your memory you are taking. Okay. Yeah. So say if you are taking 1000, okay. Say then the space would be 1000 bytes. I'm saying that say each byte stores 1 unit of number or 1 unit of data. Okay. For simplicity, it might be 4
হ্যাঁ,
bytes, whatever. For
তার মানে
simple case.
এটা হচ্ছে এটা হচ্ছে লিনিয়ার স্পেস কমপ্লেক্স।
No. Listen. That should be linear, right? That should be linear. But in space complexity, it is quite trivial that as your input size grows, you are going to be using at least that many bytes of data to store it. Okay. So it doesn't make sense to start everything from linear. Okay. So what they do that it is already assumed that if you take 1000 bytes will be used, 10,000 bytes will be used or something like that. So in the space complexity, we tend to analyze, say, other than the simple base storing unit, do we need any additional storage? Okay. Do you get it? So is there any copying action happening? Additional means you will see in algorithms where you need to store, let's say merge sort. Okay, like here. Let me go here. You will see what happens in merge sort. Let me play that animation real quick so that show you. It not only splits the array, so as soon as it splits the array, it is also storing the array. Okay, that means there is a storing or a duplication of array or a duplication of the half of the array. Okay, because this duplication requires additional space, that space is used or is counted in space complexity. Okay, whereas in bubble sort, it is swapping directly in that location, so it never actually requires additional space. That's why the space complexity looks for that additional space. Okay. Yes. Correct.
লাইক আমি প্রোগ্রামের লজিক ভাববো না, এটা ভাববো।
Okay, so that's a good question, that should I also think about the logic and also this space complexity in the not only in the earlier days, but when you do a lot of this systems programming. Okay, systems programming means where your program when scaled will affect how much resources it will take, and that point now, not only your logic but also how much resources you shall be using is a very crucial thing. Okay, a good example would be, let's say, AWS. So AWS basically means Amazon Web Services. They write their VMs, that's mean virtual machines, in, let's say, using hypervisors and all this. Not going into that, what are hypervisors and stuff, but understand that they write their programs or codes in such a manner where they will not only have the most fastest, let's say not in sorting, but fastest operations, but also will take the least amount of space or least amount of compute. Okay. So not only they have to optimize for fastness or quickness, but also they need to optimize for reduction in the number of computes, that is a time complexity, and also in the reduction of how much storage it's going to take. But because AWS has a different way of approach, they are not caring that much on the storage, so they take a liberty on the storage and basically optimize for the time compute. Whereas Azure, if I know correctly, they do a little bit more of this space complex. They take care of space complexity better. Okay. But again, Amazon Web Services are way more reliable than Azure. But I should not be saying it on a stream, but I don't know. That's just how I have seen through the statistics, but again, it might have changed. Okay. Because they are updating their whole algorithms and everything, almost everything. Okay. So that's there to it. Now, merge sort algorithm basically splits the array in the left and right path, and it goes till the end and basically finds that in the last remaining two elements of that merge sort, like the small array, how do we arrange them? Okay. And then after arranging it, it merges them. Okay. And merges them and creates a new array, and basically it goes in the backwards. Okay. To create the sorted array from those dividends or divided halves. Okay. So this is the algorithm. I'm just keeping it here. You don't need to worry that much. Now then we have the quick sort. So do we have a quick sort animation? Yes, we have a quick sort animation. And quick sort again implements a divide and conquer rule. So what is a divide and conquer rule? It basically means that your algorithm will split the array into multiple smaller sub-arrays so that they can be computed, or let's say any kind of computation or comparison can be done on those sub-arrays faster, because we are solving smaller chunks of the problem, not the actual problem as a whole. Okay. So understand the quick sort has a like average time complexity of n log n, which is currently better than insertion sort or bubble sort or selection sort, which are in quadratic. Okay, but is it better than merge sort? If you look carefully, in merge sort, the time complexity is n log n in all cases, the best case, worst case, whatever be the case. Okay, but if you look at the quick sort, in the average case, means when it is having some, that entropy graph. Okay, so in like where average of those cases lie. Okay, Gaussian graph. Okay, so let me show you.
এই গসিয়ান মানে কি ওই ইলেকট্রিক ফিল্ডে গসিয়ান বদল?
No, this is the mathematician Gaussian. Okay. Okay. See, suppose you have a lot of arrays. Okay. And in those arrays, say there are, so don't worry about these percentages that much. It's with respect to the standard deviation. Don't worry about that. Just look at the curve. Okay. In the curve, you will find that as you, let's say, don't even bother about the x-axis or y-axis. Okay. Just understand the theory in a very raw sense. Okay. What I want is that as my input is getting disordered. Okay. Yes, standard. Yes. This is that standard deviation. Correct. And these are something called z indexes. थोड़ा बहुत ज्यादा स्टैटिस्टिक्स हो जाएगा अभी 11-12 के लिए, थोड़ा छोड़ दो, ठीक है। इसलिए बोल रहा हूँ, डोंट वरी अबाउट द नंबर्स, बस कर्व का नेचर देखो और मजे करो। देखो नाउ क्या बोल रहा था, या एज योर इनपुट गेट्स slowly and slowly disordered. Okay, disordered, I mean that say there are only two cells which are interchanged, then there are four cells which are interchanged, then there are five cells which are interchanged, or let's say a Rubik's cube. Okay, so Rubik's cube, if you can solve it in, let's say, one swipe, means if you just rotate one rotation. Okay, if you can solve it in one rotation, that means the previous configuration and the new configuration uh, are not that much disordered. Okay, it is very much ordered. Say you need two swipes, then it is a little bit more disordered. Then you need, let's say, three swipes, I mean, in the sense, three rotation. Okay, if I use swipe and rotation, please interchange them in your minds. Okay, so then you need three rotations, then you need four rotations, five rotations, and all this. So as the number of rotations increases to solve the Rubik's cube, don't you think that Rubik's cube is becoming more and more disordered, right? So if you require 10 rotations to solve a Rubik's cube 1, and say you need 100 rotations to solve Rubik's cube 2, then I can say that the Rubik's cube 2 is way more disordered than the Rubik's cube 1, right? So that is a metric in which you can say that yes, and now that I'm telling you thermodynamics, because there will be stability factor and all this, which I'm not going into. You will see that I'm ignoring the stability as much as I can at this level. But yeah, I was saying that. क्या बोल रहा था? Yeah. On a very average scale. Just yeah. Okay. Okay, on an average scale, say you have a Rubik's cube which needs somewhere in the middle, let's say 20 rotations. Here, let's say 20 rotations, here it is 18, here it is 22. Okay, so in this particular range, in 1 sigma or 2 sigma, sorry, not 1 sigma, let's say in some distance. Okay, in some distance, your Rubik's cube lies the average case. Okay, which is, let's say, in 20 or more or less 18 or 22 rotations, you can solve it. And here comes the 1 or 2 swipes. That means it is way more ordered. And here it comes where you need to do 100 swipes or 100 rotations. Okay, understandable. So in that sense, a average case means how many swaps or how many, let's say, merges or how many, let's say, insertions, okay, whatever be the operation in that particular algorithm, which is the most expensive operation. Okay, so for bubble sort, it would be the swapping operation. For insertion sort, it will be taking that element and then inserting it on the back, that particular operation. So whichever operation in that algorithm is the most expensive, how many times you need to do that operation on average gives you the time complexity for the average case. Is that understandable? Okay, Dutika, was it understandable to you? If not, you can ask questions. Okay, or if you want, I can repeat it.
Understood.
You understood. Okay, very good. Now that we are over the what are average case, what are worst cases. So what is the worst case? When your array is completely in the reverse order. Say you wanted to sort the array in the ascending order, it is given to you in the descending order. Okay, that is the worst case. Now, you will find that merge sort, all the cases were n log n, but in quick sort, the worst case is n square. But see the space complexity. See the space complexity in this one, merge sort, it is O of n. Whereas in this, where is it? Sorry. Yeah. Whereas in space complexity of the quick sort, it is log of n. That means it has a way better space complexity than merge sort, but again, it has a worst case time complexity. Okay. So there's a, what do you call this, kind of, yeah, that's the point. When to use which algorithm, I will come to that. But just understand, I want you guys to note it down, that choosing between these algorithms, quick sort and merge sort, if those two are available to you, you need to understand that do you have, what's the amount of storage, or let's say how many input size you have. Say you need to store a huge amount of data, then even though the worst case might be n square, but because you need to store a huge amount of data, you would prefer quicksort. But say you don't need that huge amount of data, it's manageable, then you would go for merge sort than quicksort. Understandable? Chalega? Okay, now how the quicksort algorithm works. Okay, let's go to that beautiful animation that we were seeing. So first, let's go to the algorithm in a very overview manner, because I think I think I didn't explain the quicksort that much, but I shall be sharing this whole algorithm files to you. You can look into it. If you don't understand, just come back, call me up. I shall explain. Okay. So now, basically, what do? You basically choose a pivot element. What is a pivot element? Imagine you are on a seesaw, right? So in a seesaw, what is the pivot point? It is at the center, right? And say I want to talk about a lever. The pivot point would be right in front, right? So there are different types of lever and all this. A pivot element basically means around that element you will do any kind of operation, either on the left side or on the right side. Okay, so understand that we will partition the array around that pivot. Okay, that means you will select an element. It's very much similar to the merge sort, but in the merge sort, you always selected the half. I don't care which element it is, I will select the half of the array. But here we find the pivot element. We select the pivot element, means around that pivot element, I will basically split or partition my array, where we will assume the smaller array is on the left side and the larger array is on the right side. Okay. Then we basically recursively sort the left and right partition, which is very similar to this merge sort. Okay. Let's see the animation. You will have a way better understanding. So you see, we select a pivot element. Okay. Okay, I think I should slow down this. Just a second. This is the algorithm. Oh. See, here first set the first element as the pivot element. Okay, so it has set the 48 element as the pivot element. Then it basically stores the indexes. Okay, so it takes the pivot index, which is 0 plus 1. So it stores the index, the store index. And for each I equal to the pivot index plus 1 means it moves in this direction to the rightmost index, means it is going to the rightmost element. If the AI means the pivot element plus 1 means the next element. Okay, sorry, it has already been sorted. Let me, no, just a second. Let me just refresh. Yeah, not the insertion. I want the quick sort. Okay, so let's just see the algorithm again. Oh, can I pause it anyhow? Okay, I don't know if I can pause it, but let's see. You take you go to the right hand side of the pivot element. So you check if the next element is less than the pivot element. Okay, or at least equal to. Okay, but there is a chance that you won't be lucky, because lucky in the sense that this is a choice based, right? You are basically blindly choosing an element. Now there are algorithms which improve over the quicksort algorithm, where they don't always blindly choose the pivot element, but there is a whole idea that how to choose that pivot element. Okay, but we are not going into deeper into that.
ভাঙছে এটা কি রেসপেক্টে ভাঙছে মার্চ সর্টে বা
March
লাইক
sort it
প্রথমে যেমন
length
প্রথমে
whatever be the length half.
চারটে কি নেব না পাঁচটা হাফ কনভার্টেশন সবসময় হাফ
Yeah, that is March sort. Whatever be the length of first one.
এখানে পিভট এলিমেন্ট কি নিচ্ছে কেউ সবসময় ফার্স্ট নিতে হবে?
Yeah, that's the point. So you can actually change. Okay, and you will be changing the pivot element as well. So point is that first choice of pivot element kind of makes a whole algorithm dependent on that, how well your sorting, how fast your sorting will be. So can you just go and look into the animation real quick? Say it chooses the pivot element here, then it goes to the left and compares with the pivot element. Okay, then goes, it goes, and 15. So none of these are actually greater than the pivot element, but it was able to basically take the last element and switch the pivot. Now it again goes. I think now the pivot element is 27. Yeah. Now it is basically pivoting and switching it out here. Now it again switches the pivot element. Arey na. Arey 38. Oof. That. See, 38 was the pivot element, right? Then it compares. See the algorithm here. See the algorithm?
হ্যাঁ সেটা কম্পেয়ার তো করছে, তারপর লাস্টে পাঠাবে ওটাকে, সেটা ঠিক আছে, কারণ সবচেয়ে বড় বলে ওটা।
Yes, and lastly, you swap the pivot with the stored index -1. What was the stored index? Pivot index +1. That means the next element of the pivot element. Okay.
আপনারা বলে এইবার এখন এবার প্রাইভেট কোনটা, 15 না 27?
বল কি মনে হচ্ছে?
27টা তো করছে, ঘুরছে তো,
এবার
27ই হওয়া উচিত। 8 এখনো তো 8ই আছে।
good. Yes. Now আবার 8 আছে, ঠিক আছে। Okay.
আবারই 8
I
আছে।
think this array is not a very good example
জিরোটা
of.
জিরোটা একটা আইসোলেট হয়ে গেল কেন বাদিকে?
See the algorithm. This OR.
ও কি বার 50% লাকি মানে
Arey,
ইকুয়াল
that's
বা
just
50%
a
লাকি?
or equal means it will be less than or equal. Okay, but having that equality is like if you are lucky enough. That's just a comment. Okay, fine.
ও আচ্ছা।
See, this is the algorithm. This is the whole algorithm. If the element is smaller than the
হ্যাঁ
pivot
ঠিক
is
আছে,
found, swap it with the greater element pointed by I. Okay,
ওকে।
this is the partition
তুমি
part.
আমাদের এতগুলো শর্ট দেখাও, সেটা সবই অ্যাসেন্ডিং অর্ডার, ডিসেন্ডিং অর্ডার এরকম শর্ট শর্ট হয় না?
Just change it. Just change it this less than equal to the greater than equal, and it will sort it in the
হ্যাঁ ঠিক আছে।
other ones. Okay, next is heap sort. Okay, अच्छा Dutika, do you have any questions? कुछ भी है तो बोल सकती हो.
No.
Are you finding it interesting or just boring? Are you finding it interesting? Boring लग रहा है तो बोल सकते हो it is boring. Okay, she's not saying anything. I don't know, but मत बोलना भाई. Okay, this is the heap sort algorithm. Okay.
ইন কম্পিউটার সায়েন্স ডেটা স্ট্রাকচার অ্যালগরিদম, এই চ্যাপ্টারটি যে হাইপ আছে না, ইউটিউবে ভরে ভরে সব হাইপ আছে।
Yeah, basically data structures and algorithm is one of those core topics, okay, which is required for any interview. Okay, that's the point. That's why it is just important. और क्या ही बोलूं. Okay, so let's start the heap sort. By the way, do
মানে
understand that
মেকানিক্যাল ইঞ্জিনিয়ারিং এর মানে
yeah.
একটা মানুষ যদি মেকানিক্যাল ইঞ্জিনিয়ারিং পড়ে সে ইন্টারভিউ দিতে যায়, তাকেও কি এসব করতে হবে নাকি ডিএসএ?
Yes, yes. So basically, at least in India or even a lot of interviews in the foreign MNCs, okay, you do need to give interviews on data structures and algorithms, okay, and you need to give interviews on graphs, on binary trees, on trie, okay. Trie is another form of the like structure, okay, which is I think in the last class I discussed that trie is being utilized in your like word correction or autocorrect or even the next word prediction, okay. So those are algorithms there, but need to understand that if you want to crack any interviews in companies, you would be very much required to solve a lot of DSA. Okay. Okay, so I'm getting comments and my friend is saying that yes, that's true. Okay. So thanks, Subrajit. Yeah. Yeah, you can take any company name. Nah, nah, nah.
বলছি যে গোল্ডম্যান স্যাক্স ম্যাকেনজিতে চাকরি পেতে গেলেও এসব দিতে হয়, ঠিক
Oh,
আছে?
no, no, no. That's a very good question. Goldman Sachs, there a lot of their interviews are hidden. Okay. But recently, one of my friend, okay, got into JP Morgan. So the interview was, it was like very difficult. Okay. They gave him a question which was based on probability and stochastics. Okay. So not only he had to know the core mathematics behind the probability, not even the normal probability that you think, or even the other statistics that you might think, but it was basically on the measure of probability. Okay. No, no, on the measure of the probabilities, means the probability metrics. Okay. So he told me that the question was a combination of probability along with stochastics of the current financial market, and where he had to apply, basically where he had to apply a game theory, basically a game-like solution. So he got that job because of applying all this thing, and currently he's at a, I think, good position. He told me his salary, and it's crazy. It's, I think, 62 LPA. Okay. Yes. Okay, so it's crazy. He's a I think I should say it. He's one of the toppers. Okay, at some IIT. Not going to really like reveal too much. Okay. Yes, it's in the top 10 IITs. I think that IIT is actually in top five. Yeah, top five. Okay, whatever. Let's continue. Hmm. Okay, now let's continue the word. Okay, the heap sort. So I haven't gone through the binary data structure. So basically it creates the, suppose you have an array. Okay, let me show this graph again. I think I should actually decrease the animation speed somehow. Where is it? Change canvas size, move controls. Okay, this is pause. Animation speed. I need to slow it down a little bit. Now, step back, play. So is it playing, or is it just too slow to even play? Heaps of. Yeah. So now, okay, let me pause real quick. So just see, 491, 491. Then basically 215, see, 215 is on the left, 215 on the left, 449 on the right child, right child. Then you have sorry, yeah, Taihoji, 285, 72. Left, right. Then 365, 286. 365, 286. So do you understand how you're converting an array into the binary tree? So basically you take in a level order. Understand the term level order. So you have the array which is in a 1D format, and you create a 2D data structure which is a binary tree. Okay. This much is understandable. And how do you create the binary tree? You take a level order traversal, understand the term, level or the traversal of the input array. So whatever be the first element, it will become the root. I'm telling the terms, so please understand those. It will become the root. And as it becomes the root, the next two elements will become the child, the left child first and the right child first. So understand that this is the left bias level order traversal. Got it? Because it will take the next element 1 and 2 as the left child first, and then the right child, and then again it will go to 215, and then it will again do the next two elements, which is 280. I think this is, I need to zoom in. Just give me 1 second. Now I think it will be way more visible. Sorry if it was not visible earlier. Now I am going to take the 285 and 72. Okay, so they are again left bias 285 and 72. So that's how you create a level order traversal of a 1D binary, 1D array into a binary tree. Okay. Hopefully that's clear to you, right? Fine. Okay. Now what we are going to do? Now we are going to basically take, let me see, skip back, step back. Yes. Oh, play. Acha, heap sort, pause. So this is the initial configuration, 186 or the last. Okay. Then step forward. You will take the last two elements, means here. So these are the leaf nodes. Okay. You will take the last two elements and then you will check it with their parent. Okay. So in those two elements, understand that parent is lying here. Okay. See where the parent is lying. So back in the whole stack. Should I say stack? No, let's call it in the array. Okay. This is the parent. Now see, compare 519 and 412. Okay. Good enough. What we are going to do? We are going to swap it. Why? Because 412 is actually smaller than 519. Okay. That means the parent node, what is the logic that we are looking for? That the parent node must be at the max position or at the mean position. You get it? The max position or at the mean position, depending on the sorting that we want to achieve. Okay. Next, we will go and do it for the next leaf and the node. Okay. 32 and 308. Again, we will compare. Okay. 308 is larger than 32. And then we will compare with the parent. So can we do swapping? No, we don't need any swapping here because 743 is of course larger than 308. Next, we will compare between 985 and 109. See, can you tell me, will it require swapping? Yes or no? Will it require swapping currently? No or yes? No, understand 985 and 459. Will it require swappings? 459 is smaller than 985. So it will require a swapping operation. Okay. It's swapped. Then again, we are going to compare. Now see. That basically I'm showing that it is moving forward to the leaf nodes. That's it. Okay. Now here also no swapping. Here we are going to require swapping. Okay. By the way, the comparison is required to understand which one of the two leaf nodes is the greater element. Okay. Yes. Next we are going to swap again. Next here we are going to swap again with the 496 and 193. So see, the first level of swapping done. Now we are going to go through the next upper level. So basically I'm going to skip forward a little bit, but see, again here, another swapping with 985 and 365 will be required. Sorry, 990 is larger. Sorry, I did not see that. 990 is larger, so there will be one swapping. Now understand that the child, because it has changed the child. So you need to again check and do the swapping if required. Okay, here it is required. Then again, you will see that 983 is larger, so it will be swapped. And because it has changed, so first do the 72, compare with the 72. So 121 is larger, so it will change. Then go to the next one. Here swapping is required because 798 is larger. Okay. Okay. I'm skipping forward. Hopefully you guys understood the first part of the algorithm, right? Understood? Chalega? I'm skipping forward. Don't if you have questions, ask me. Now here is the main part. See, slowly and steadily, because you are swapping in this heap structure, your whole tree is getting sorted. Okay. With the largest element coming at the leaf nodes. Okay. Can you see that? The largest elements are slowly coming out to be there at the leaf nodes. Okay. So now I'm going to basically increase the speed and let it play. Yeah, so this algorithm generally you learn it. Yeah, so basically you need to understand binary trees a little bit before you write the algorithm of it. Uh, I would like to ask, at least try writing it. Okay, try once writing it. My notes will be there. It is set with you guys. Do not need to worry. Okay. Uh, but generally it is taught to people in the second year. Okay, second year of any BTech or in the first year of ISI or any maths course. Okay. Yes. So this is the whole algorithm. Okay, it's already there. These are actually taken. At the end of the day, we also had to pass through the course and we had to write this whole algorithm in C program. Okay, in C. You need to understand. We had to write this whole program in C uh, without any help on Vim. So there were not even any kind of this is the heapify. Basically, heapify a subtree is basically create the heap. Okay, heap. This is called what do you call this? Sorry. Um, how can I make it understandable without going into the terms? Hmm. This whole structure, okay, where you have some element at the max position as a parent, okay, or the min position at the parent. Currently here it is a max CP5, okay. It is max CP5 means the parent is larger than the children, okay. So this is max CP5. That kind of structure is called a heap, okay. Got it? Now we come to interesting algorithms, which are non-comparison sorting algorithms. Okay. So the first algorithm that we will do in this particular whole series or the next series, which be the counting sort. So counting sort is a sorting technique which is based on keys between a specific range. It works by counting the number of objects having distinct key values. Okay. So what are keys? You can imagine it as sort of doing some form of hashing. Okay. So for how it works, it basically first finds the range of the input, then it counts the occurrences of each element in that particular array. Okay. Then it builds a cumulative count of that array. Cumulative count means okay, ये element इतनी बार आया, ये element इतनी बार आया, इसका frequency इतनी बार. You know, you have done that frequency table in your class 10, right? Both of you have done that frequency table, right? Array, finding
1 by
that
time period.
average. Yeah, no, not 1 by time period. At the end of the day, that is frequency. I'm talking about mean median mode, that chapter. You would have done cumulative frequency, right? So it basically builds a cumulative frequency for all this. Okay. And then it places the elements in the correct position based on that cumulative frequency. You can see the algorithm real quick. Let me show the simple one, or let me show the simple one. Okay. No, there is no comparison. See? Done. See, this is very simple actually. Counting sort is very simple. Let me zoom in. Can you just see the algorithm and just tell me? It's you can just look at the algorithm without even knowing too much. It's like भाई किसी ने सोचा कि अरे भाई ऐसे भी तो कर सकते हैं, and it works. Okay. See, for each element in the list, increase the respective counter by 1. Means you do a counting array for each element. Okay. Then what is there? For each counter starting from the smallest key, while a counter is not 0, of course, otherwise it won't make sense. Restore the element to the list and decrease the counter by 1. समझ में नहीं आया तो समझ ले कि एक लिस्ट है Okay, there may be items which are repeating. Okay, so if there are repeating items in this particular case, as you can see, 5 is repeating twice, 1 is repeating twice, 7 is repeating twice, 0 is 1, 3 is 1 time, 6 is 1 time. Okay, let me do the sorting. Simple. See, this has been arranged in like this. Okay. Oh, I can, if I can just pause this page. This is a very nice website, but it has no pausing. Yeah. Can I do the Aste? No, I can do the speed up, not the Aste one. Sorry. Can I do anything else? Okay. See, it first builds up the see, it first builds up this frequency table. Can you see this? See, it takes all the array and creates a map. All the elements of the array and creates a map. Okay. Oof. Wow, that was very quick actually. I think it somehow, it is actually quick. It first builds this map, okay, where it then goes element by element and counts कितनी बार आया, ठीक है? Okay, let me show you again. हर एक element है, then it builds a counting map. Okay, so understand this part. It has a very bad space complexity, by the way. Okay, because these indexes are based on, see, 2 is here, 3 is here, 4 is here, 5 is here, 6, 7, 8, 9. Because the elements that we are actually sorting gives you the indexes, okay, or indices. So if it is 9, then it will go to the 9th index, okay, and that 9th index ka value will increment by the number of times it is coming. Okay, so say this is 9, okay, and 9 is coming up 2 times. So it will build another array where at the 9th index it will put 2. Do you get it? Yeah.
সবচেয়ে প্রথমে শর্ট আছে
So
ওরম ভাবে
if
এটা করছে
one occurrence of 1 is 4, so if there is another array in that 0 and the first index, so the first index basically means यहाँ पे value क्या है 1, and in the first index it will store the value as 4. Okay, like okay, understand. I know this is might be a little bit difficult. Let me go to the simple one. Okay, can't I actually pause it? Oof. Okay, see this. See this. Here I have what? I have 1 and wait.
এটা কি হচ্ছে
Oh, that is just some glitch. Okay, don't worry. So, oh wow, it is actually faster than me clicking. Okay, now the point is that you have 0, 2, 1, 9. I don't care. I don't care where the elements are. I'm not even going to compare. What I'm going to do, I'm going to build another array where it will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And say there is some, oh wow, that is nice. So basically I'm not letting it go. Okay. Wow. So you have this array and I build another array where I take the values of the initial array and place it as indexes in the another array. Okay, so say another array is here, so there is 0, 1, 2, 3, 4, 5. Then because it has a value 1, at the index 1 I will have the number of occurrences. ये तो समझ में आया, right? This is understandable, right?
ঠিক আছে
And because I have let's say the value is 2, do I have 2 anything? 2. Yeah, 2. Okay, so at the 2 index in the new array it will have a count of 2 because there are only 2 elements, like 2 is coming twice. Okay. Then at the count, then 3 in the new array, in the index 3, are there any occurrences of 3? No. 0. Are there any occurrences of 4? No. 0. Are there any occurrences of 5? Yes. 5 is occurring once. Are there any occurrences of 6 here? No. Are there any occurrences of 7 here? No. Are there any occurrences of 8 here? Yes. There is only one occurrence. Then are there any occurrences of 9 here? Yes, and then 9 will be 2. Then it will go to the new array where the 0 occurrence is 0. Then it will see that, oh, acha, first index mein 4 bar aaya hai. So it will basically take out 4 ones. Then it will take out 2 twos. Then there are no elements to take out from 4, 3 or 4. Then it will take out the 5, then 8, then 2, 9 from the new array. Okay, that's how it works. So it has a very high space complexity. Yes, sure.
এখানে 0 থেকে 9 নিয়েছে, বাট আমরা কি করে জানবো এটা কত থেকে কত নিতে হবে?
Here you will find the range of the input. Okay, so in the first stage you need to find the smallest element and the largest element. See, minimum value and the maximum value. You need to find the maximum value or the minimum value in the like whole array. Okay, that is one point. That's the okay. Hopefully that answers your question. Okay. So after you get the input of the range, but basically find the range of the input, then you implement this whole, basically you take the original array and build another array and just print it out. That's it. Okay. Then there is another way of sorting, which is the radix sort. Okay. This is the radix sort. And थोड़ा complex हो सकता है. Okay. What is radix, by the way? Radix basically mean base. Okay. In computer science, radix basically means base. Oh, wait. Am I having any networking? Okay. Give me 1 second. There might be a network issue that is going on. Hopefully the network issue has been resolved. Am I still in the meet? Yeah, I'm in the meet. Okay. Okay, so let's continue. Radix. Radix basically means the base. Okay. And in that particular base, what do I mean? I mean the total available symbols in that particular representation system. Okay. You can see that what the definition is given here. Radix sorts numbers by processing the individual digits from the least significant digit to the most significant digit. That means from the LS. Generally we say LSB, basically LSB for byte, but here we are talking about digits. So basically it might not be in the byte system. It might be in a, let's say base 16, base other bases. Okay, so we say LSD and MSD. Okay, so there is another meaning of LSD, but at least we are not talking about drugs here. Okay, so now what it does, it basically finds the maximum number to determine the number of digits. Okay, so first it goes for the maximum number. Then for each digit position, be it units, tens or hundreds, it basically uses the counting sort to sort that digit. Okay, and it repeats until all digits are processed. Let me show you the animation. You will understand what is happening. Okay, it's quite fast actually at this point. Or maybe my this website is broken. We see. Yeah, this website was broken. So what are these? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What are these? Let me
These
show you
are
the
numbers.
algorithm. By the way, do you remember for Dutika, I think I haven't done the queue data structure, right? It uses a queue by default. Hmm. So I'm telling you what a queue is. A queue is a data structure in which the first person who comes first will be served the first item. Means it is served first come first serve basis. Okay. So a queue data structure, you will see that. Let me do the sorting again. You will see that there are multiple buckets or multiple places where, say this one, 8. So here the first person who came was 7041. So you will see that the 7041 came out of the bucket first. Okay. So this is a queue. Whoever came into the bucket first will also go out of the bucket first. This is the queue data structure. Okay.
7041 fourth ইন্ডেক্সে কেন গেল?
That's why you need to understand this digit algorithm. For each digit placing, okay, for each E in the list, move the E into its bucket. So now let me go to the sort again. So 7041, 8251, 9501, 1 এ গেছে, means the last digit is ending with 1. Okay. Fine. Yes. Fourth index কখন গেছে? Oh, আচ্ছা ওটা, that is because it is doing the recursive, right? So see, for each digit E in the list, move E into its bucket. Means this loop will go on for each digit. So first, in the first loop, it will take the last digit. In the next loop, it will take the second last digit. In the third loop, it will take the third last digit. Okay. Then what happens? As it takes the digit, it puts them in a bucket of priority lists. Okay. Then for each bucket B, starting from the smallest digit, while B is now empty, restore the E to the list. Means it will first create buckets of all the digits possible or all the symbols possible. Okay, that means in a number system where you have 10 digits possible, which are 0 to 9, that means it will first look at all the numbers that it has available to, or it needs to sort with. Then it will go and check which particular number ends with 1, which particular number ends with 0, which particular number ends with 4 or whatever. Okay. Then from left to right, as it scans, it will go and select out, okay, the first number that ends with 1 will go into the bucket. The next number that ends with 1 will go into the bucket. Okay. Let's just sort it again. See, when you it from the left to right, it's too fast at this one. Can't I actually adjust it? Ready sort. Okay. Just focus on the 1, or I think in this particular example, I don't have 1. Focus on the 8. Okay. So there are only 2 8s. Now it basically removes the list from the items from the list. Okay. Now it has removed based on the not even comparison, the order in which these two came. Then the next digit, which is 6. Okay. So 6, it only has 1 6. Okay. It came out in that particular order. Okay. 6, it came out. Okay. Then 4. So it will go to the 4 here. See, it came up to the 4. Okay. Where they have the 4 in the third last digit. Okay. Now what it has again 4. So it will again go to the, yes, queue. It is coming out in the form of queues. Okay. If you look at the algorithm smartly, you will see that this is a wonderful algorithm where just by having the number of digits, means the number of available radix or base, okay, you can sort any array of any number. So it's one of the more efficient algorithms. Okay. See, what is the time complexity? The time complexity is linear times the number of digits, which means the number of radix or the base. Okay. Fine. It is suitable for large numbers with small digit count. Okay. And it is quite stable actually. Next, there is the bucket sort. I don't think I have this random quick sort. I think bucket sort is the last one. Yes, bucket sort is the last one. Let me show you the bucket sort. Yeah, bucket sort visualizer. Of course, they have made it. I think this was actually a university project of USFA. Okay, and it's an old project where they basically gave uh, the programmers. I think this was given to the second year students, if I'm not wrong. They have a bunch of their lectures uploaded where they gave this assignment to the second year or third year students, no, second year students, where they have to basically build a visualizer of each of these algorithms in JavaScript. Okay. And after that, they open sourced the whole project and hosted it on their website. And it's so good. It is helping millions of students all across the globe. Okay. So let's start. So you see that this is a bucket sort. Okay. It's a very fun algorithm. Let me zoom in. Skip back. Let's put the animation speed at a very slow. This has a very good animation bar. This is required. Okay. So bucket sort, you will pause it. Okay. Now see, there is a bucket and it takes the first element. Okay. Now it has taken the first element. See this thing. Linked list. Oh, by the way, yeah, I totally forgot that you need to have the concept of linked list here. Dutika, there? আছো তো? So, do you remember anything that I told you about linked list? Or should I repeat? Yes, sure. That's why I needed that confirmation. Let me repeat what is a linked list real quick. So here it is. See this. The internet speed is slow or something. So here it is a linked list. You have a head. So this head is a pointer. Okay. It looks or it basically stores the address of the first node of the linked list. Okay. And in this node, it has two partitions. One partition stores the data, which is 11, and the other partition stores the address of the next node in the list. Okay. So because it stores the next node in the list, it is only storing one element in it, or let's say at most two if you count the data as well. Now, after that, the next node is storing the next node in the list. This is the next node is storing the another next node in the list. Okay. And it goes on till the last node, which stores no address in its own data, or sorry, in its own address path. Okay. And that address path, we call it as link or we call it as next. Okay. So this whole chain, like a garland, okay, is what we call as a linked list, like the mala of the sages. Okay, it's something like that. There are different types of linked lists which have something like the doubly linked list, where not only stores the address of the next node but also stores the address of the previous node as well. So there are different types of linked lists. There is also a circular linked list where it not only stores the next node and next node, but the last node stores the address of the first node. So it completes the whole circle. That's why there is something called a circular linked list. Okay. So hopefully the basics are clear. Now, let me go back to here. So what happens? The linked list array index is the value times the number of elements divided by the maximum array value plus 1. So here what do we have? We have the value, which is 22. Now the number of elements. So there are 30 elements. You can see the index starts from 0 to 29. So there are 30 elements. Okay. Then the maximum array value means in this whole array, what is the maximum array? Yeah, maximum array value plus 1. So what is the maximum value? Can you find it? Maximum array value. Is it 949? Why is it then 1000 divided by maximum array value? Am I missing something? Wait. I actually don't. Yeah. Sort each bucket individually, concatenate all the back buckets, and there is. Can you just give me 1 second? I remember correctly that it was the maximum value in the list. Why is it not like that? Largest numerical element present in the input array. Yeah, true. So is there 999 somewhere that I am not seeing? Or it's being printed wrong? 949 is there that you just told me. Okay, let's continue and see why is it there. Step forward. This 22. Next bucket is 614. Why is it? Is there something wrong here? Am I missing 999 somewhere? Let me see. This is the bucket array. Hmm. Yeah, it is. It is the largest. Yes. Just give me 1 second. I myself need to read some Stack Overflow. Either their implementation is wrong or I am thinking something wrong. But for example, if the mean is negative 25 and max is 25, then you have to create 51 buckets. Yeah, that is true. And then you have to create 30 buckets. Yes. So yeah, that is a number of buckets, but not asking something like that. This sorry for the background noise. In the context of bubble sort, the maximum array value refers to the largest numerical element present in the input array that needs to be sorted. Total and the number of desired. Yes, I then why is it like this? Acha, can you just compute this 614 times 30 divided by 1000? Is it coming out to be 18? Wait a second, let me check it on my calculator real quick. 614 times 30 divided by, yeah, it is 18. Well, 18.42, which you need to basically discard the rounding error, not rounding, like that part. Wait. I think what they are doing is, no, that is not even correct. If they're doing it like 30 plus 949, that is what? 950, 989 plus 1, 990. 990. That is still not making sense though. How is it? They are doing something wrong here. Should not be like this. Sorry for this. I did not check that there was some error in that particular website. Yes, this is the pseudocode. So for any bucket sorting array, you basically need to create a new array of the k empty list, move the array, insert the array into the buckets, floor of the array divided by m. So m, they discussed what is m here. I think they should have. This is the max for it. If you are interested, you can look into it. Where is m? Generally, m means the largest element in the array itself. So I never thought about this too much. I thought that they have computed correctly. Let me do one thing. Go back to the heap sort, not heap sort. कहाँ गया? Bucket sort. Let me refresh this. So this is a new array, or maybe that array itself. No, this is a new array. So if I just start, oh, this is again by 1000. Oh, pause. Now I get it. Okay. So probably they are dividing it by 1000 as a constant number, because in their own assumption, what I'm seeing is that the largest element, see, the largest element is probably 900 and something, 957, right? This is the largest element. So they're rounding it off to 1000 just for computational simplicity. Otherwise, it doesn't make sense for it to be anything else other than 958. Okay. What I can say that they probably are doing it for the sake of simplicity, but I shall confirm it why they are doing this here, or if there any kind of approximation is allowed. Generally, what in my program I used to do, I always used to find a maximum element and then I used to divide by it. Okay, but why they are doing it with 1000? Probably just to do an approximation over it. Okay, so if we can take that little approximation as all right, fine, chalega, then we can basically continue with our algorithm. So what they do, they compute this, the value of the next element times the number of elements, which in this case is a 30 element array, and you divide it by the largest element, which they have rounded off to 1000. And of course, while you do the divide, you do an integer division, means whatever be the integer closest to it. Okay, not even closest to it, it's like discarding whatever comes after the point. Okay, so if it is 8, at the 8 index in this bucket list, you will go and put the 287. So step forward, and then you have the next element, which is 293. So 293 times 30 divided by 1000. Okay, you will see that, okay, these are the these two are coming in the 8 location. So then at the 8 location, 8 is like a head. Okay, so it has started creating a linked list. Can you see the linked list that is forming here? Both of you, can you see the linked list that is forming here? Chalega? Okay, next part. Then we have 583. 583 times 30 divided by 1000, 17. So you will see that it is forming another linked list, 571. So then it will go to 17 again. Okay. So see here, you basically do the comparison and always put, this is what? This is insertion at a location, right? Insertion at the position, at a desired position where the new element is lower than the previous element, or basically you compare where it should be. Is it in the before or the after? Okay. Then you take 341. I think this will again go to 8 or 9. Oh, it goes to 10. Okay, 341 times 30 divided by 1000. It becomes 10, so it's fine. That's a good number. 167. It will probably go somewhere in the 1, 2, 3 or 5. Yeah, it goes there. 477. 477 times 30 divided by 1000. Yeah, that's there. 14. So then 130. 130 probably go to 4 or 5. So it goes to, it goes to 3. 130 times 30 divided by 1000. Then 375. Let's see, it goes to 11. Okay, that's good. Then 100 will go to 2 or 3. Yeah, it goes to 100 times, that's 3000. Yeah, that's 3. Yeah, that's exactly 3. 682. So I'm playing forward the animation so that you can see that it's taking one element times the 30 divided by the largest element which they have approximated. That's what I think that they have done in this visualization. Okay. So as you can see, it is continuously building a linked list. Okay. At all these locations. Increasing the animation speed a little bit. We are just now left with 5 more elements. And you can probably guess what's going to happen in the next part. This is the last element. Yeah. Now basically put all the elements in the order. Okay. In the order of the buckets, and not only in the order of the buckets, but as you go from one bucket to another, you also print, or let's say put the elements in the order of the linked list as well. Okay. See, basically you are deleting or popping out the list from the front. Okay. And as soon as you're done with all the buckets, voila, you actually have a sorted array. So this is called a bucket sort. Okay. This has been implemented here. Now, after all these are basically done, we are now finally at the last part of this whole segment where we will do bubble sort, selection sort, insertion sort, merge sort, quick sort, and heap sort. Why we are going to go into these? Because these are comparison based sorting algorithms. And what we are going to do, we are going to run a benchmark. Okay. We are going to run a benchmark here. See how basically they are going to be performing, and you will see that I have taken the array size as constant, but after this I'm going to come when to use which algorithm, but quickly I want to show you the plots. Yes, these are the plots. See, okay, I think I should run this again. Just give me 1 second. Yes, these are generating now. Give it some time. Yes, done. So here what we are doing, we are taking a theoretical time complexity comparison, okay, between what we could actually see. Here you can see that this is the constant time, big O of 1. I think, can you see this? Big O of 1 here. This is the big O of 1. I don't actually know which color you call it, probably orange or something. After that we have log n. Okay, after that we have this thing which is linear, and then we have n log n, and finally we have n square. Okay, these are the different behaviors. But now see this. I want you to particularly focus on this particular point. Okay, this point. Can you see this part? So there is a region where you will find that this n log n, okay, is performing worse than the n square. Okay, so take this as a homework, that up to which input size n log n performs worse than n square. Can you find it out? Can you find this? So take it as a not a computational homework. Take pen and paper and find out the number at which n log n performs worse than n square. Got the homework? Can you see this? See this. The more the graph is on the left hand side, or towards the upper part, the worse is the algorithm performance. So we know that n square is bad, right? N log n is better. But there comes a point before which you will find that n log n is performing worse, whereas the n square is performing better. Do you get it? So I want you to find out which exact point that is, after which this twisting of, let's say this swapping of fate occurs. Okay. See, it is not. It is near to 60 or something. Okay. So I want you to find this point. I could find it computationally, but I want you to find it theoretically. Okay. Dutika, do you get the homework? Okay. It's a simple inequality, right? You can do it. Next is a comparison over. Yeah, you can. Of. Acha, next. Yeah, next. Yeah, sure. Oh, good question. Try with two. One take log 10 and another take log base e. Okay, natural log. And do you know why I told? Okay, no, not natural log. Take one more. Take 3. Well, 3 means another one. Take log base 2. Okay. Because what question you asked now is a very good question. Uh, Reason I'm telling you to take 3 different logs, I'm going to explain in the next day when you give me the values. Okay. And with each algorithm, I will show you that you can do optimization at the bitwise level, at the memory address level, where you will find that each logarithm will have different performances. Okay. Yeah, base 10, base E, and base 2. What is the value of E? Euler's constant. What's the value of Euler's constant? Ball. Value কত?
2 point something হবে
2.71.
2.71
Yes. Okay, now see this growth rate comparison of the time complexity. Okay, so as you can see, because it's basically like taking the derivatives. Okay, so when you have a constant time, of course, there will be no growth rate in the time comparison. But you can see log n, basically it has 1 by n, and basically you take the derivative. Okay, that's how you will see that the growth rate of this kind of time complexities gives you an understanding that how or rather to say when to use which algorithm. Okay, because as your input size grows larger and larger, which algorithm will perform better depends on what you choose. So in this particular part, you will see that this O of n, this part is currently performing, the growth rate is larger than this one, which is the n square, which is of course like I was telling you that n log n and n ka you can basically find a difference. But at certain position, this thing flips. You get it right. At one point, this thing will flip. One will perform better than the other. So even in the growth rate comparison, you will find the flipping. Now, this is another chart which is very important for you. This is a performance chart where you have random input performance. Okay. So here you will find that we are comparing between different comparison based algorithms, sorting algorithms. One will be the bubble sort, selection sort, insertion sort, merge sort, quick sort, and heap sort. So what happens that as the input size grows larger, you will see that this one, which is the quick sort, it stays relatively consistent with n log n, but something weird is happening here. Look at merge sort. Merge sort went from somewhere when the input size was like what 5 or something, I think 10 it took. After that it goes high, but as soon as the size grows larger and larger, the performance kind of stagnates and becomes better. Okay, this is a very important thing that you need to understand, that some algorithms perform better when the input size grows larger. Now next, look at these two. So let's say we look at the selection sort. So selection sort, when you compare with respect to the insertion sort, you will see that at some point selection sort was performing better, but after a certain while you will see that no, it is starting to flip. Okay, you get it right. At some point it will start to flip, whereas the bubble sort is of course the worst. It is n square, no comparison. It is the worst. Okay, but now this was what? This was random input. Now there is the sorted input. That means the input is already sorted. The input is already sorted. You don't need to do much work. But then also you will see that the bubble sort performs the worst. See the time scale. See a time scale. Bubble sort performs the worst. Then selection sort. Then I think this is star, means star would be heap sort. Okay, heap sort. Then merge sort. See, merge sort used to perform better here. Okay, it used to perform better when you have a random input. But see, the merge sort performance remains kind of stagnant because merge sort is n log n always. So no matter it is the best case, worst case, whatever be the case, it will always be stagnant. Okay, whereas in best case scenario, you have bubble sort which goes to linear time, and this instance sort which also goes to linear time. Okay, now this is the reverse sorted, means the worst case. Okay, this is the worst case you can give to any of these sorting algorithms. Okay, and here you will see that the merge sort performs very good, and after that it is heap sort, and after that this is the, I think, selection sort. No, yeah, this is selection sort, and after that you will see this is a turn of events. I think no, not turn of events. They were almost equivalent in the sense insertion sort and quick sort were almost equivalent, but then they kind of diverged a little bit. Now then nearly sorted inputs means the inputs are almost sorted, and this metric gives you the stability, a little bit understanding of the stability. See how the graph works. See this one. The stability of this algorithm, which is, I think, insertion sort, is not really that high. It is not stable. It should have going through like this, but it is not going through a perfectly ordered curve. Again, we see that the stability of these curves are not, well, the stability of this algorithm, which is this one, bubble sort, is very high. Also, stability is very high. Of course, it is bad, but it is stable. Okay. And this is the type of inputs that we use for the analysis. And this is the last one. Bringing it, I think, yeah. Yeah. So before I go here, let's go and discuss when to use which algorithm. That the question, I think, in the beginning of this whole session, I think Dutika or Niket, someone of you asked me. Give me 1 second. I think I put it here. When to use which algorithm? Yeah. Now the small data sets or small data rows, when it is less than 1,000, you can use insertion sort when the already partially sorted data, and selection sort, simple implementation, and bubble sort for only educational purposes, because remember, bubble sort will perform the worst. Okay, it will perform the worst no matter the case. Okay, so be very careful when you use this bubble sort, only for your educational purposes. Okay, now for medium data sets, that means somewhere between 1,000 to 10 to the power 5, you will mostly prefer merge sort. I would prefer merge sort because it's quite stable. Okay, and quick sort. Okay, for large data set where you have like 10 to the power 5 zeta, you tend to prefer merge sort, quick sort, or radix sort. Okay, there are special cases where you will prefer counting sort or radix sort or bucket sort when you have different kind of distributions. Okay, say a small range of like integers or large numbers with fixed digit count. Okay, means the digit count is fixed, means 4-digit cage, or like there are 10 lakh rows or something like that, but all of them are kind of having the fixed digit count. Then you will prefer the radix sort. Then because radix sort is not that stable when you start having different number of integers, or different number, not integers, different number of digits. Okay, so one is 4 digits, one is 5 digits, one is 7 digits. So when you have a mixed data set like that, radix sort is not really good. Then you have bucket sort, which is kind of uniformly distributed floating point numbers. Okay, it works best when you have a floating point number distribution. So if you need algorithms which are stable, which will always work, okay, then always go for merge sort, bubble sort, insertion sort. And if you are okay with some unstable algorithms, though I have put quick sort here, quick sort is relatively stable when you count. Oh, sorry, bubble sort. Yeah, bubble sort is sorry. Sorry. I was speaking something wrong. I confused between bubble sort and quick sort in my head. Sorry. So stable algorithms. Stable algorithms means where the output of the algorithm will always give you the sorted array in a consistent manner. Okay. Not only all of these algorithms will give you a sorted array, but say as the input grows larger and larger, you need that stability. You need that if I give 10 lakh inputs, if I know it will scale linearly, I will get the output at 10 lakh seconds. But say the algorithm itself is not that stable. Say, for example, the heap sort, it is not that actually stable, or selection sort. Then instead of getting at 1 lakh seconds, I might, if it's gives in a linear fashion, for example, then I might get it at 1 lakh and 100 seconds. So that inconsistency when I'm going to get the output, that sparks the instability of the algorithm. Okay. Got it? Fine. Okay, now these are the common pitfalls where you will have infinite recursion, stack overflow, memory exhaustion, and incorrect handling of duplicate elements. There are techniques where you can actually, bolo. Yeah, just give me some a few more minutes. So there are actually optimization techniques where you can apply those techniques over the already pre-existing algorithms. Say any of these sorting algorithms like hybrid approaches, where you use insertion sorts for smaller subarrays in another algorithm, say quick sort or merge sort. That means you already have an algorithm with say merge sort or quick sort, and inside that algorithm you need that sorting, right? Sorting approach. So inside that algorithm you use insertion sort. So you are mixing two algorithms where you are using a algorithm which is efficient for smaller arrays, and you are using another algorithm's divide and conquer rule for splitting the large array into smaller sub chunks. Okay, so that is called hybrid approaches. There is also like three-way partitioning approaches for arrays with multiple duplicates, where you basically partition it instead of two-way, or you will do it in three-way. Okay, and there are adaptive algorithms that basically work to detect that if the array is already partially sorted, then it will not work in that partially sorted phases or paths. Okay. Then we have different testing strategies like unit test. So in your class 12, kindly Niket is already in class 12, but I will be teaching, or I shall try to teach how to write tests. Okay. So there is a Python module which we call as what they call is PyTest. Okay. And using that module, PyTest basically helps you to run tests on your already running code, or let's say the code that you have written. It performs a lot of memory tests, a lot of, let's say, stability tests. Okay, but you need to write that unit test yourself. So don't worry, I shall probably be teaching it in the next few months, or probably after your boards. Okay, not in your syllabus.
After your board,
If you want to learn it. Yeah, for your joint exam I can't do anything, but I shall try to teach and explain those things. Okay. For Dutika, it will probably be in her class 12. I would be teaching her how to write tests. And I think if you can complete all that part, you would be very much good to go to not only write unit tests, but also to contribute to open source development in a lot of different repositories. Okay. For Dutika, I'm saying because she has been studying since class 11, since the first day. So she has got this first mover advantage in some way. Now let's go to a little bit more into the mathematical analysis of sorting algorithms, which is the big O notation. I'm not going to go in depth, but what is a function is called the big O of g of n if there exists some constants c and n not positive constants. Okay, such that it can be squeezed between these two. Okay, not squeezed, but if f of n is less than or equal to c times g of n for all such n greater than equal to that n naught. Okay, you will see that this definition is very much similar to the definition of limits. Okay, I don't know if you guys have read the actual definition of limits, but not talking about that definition that physics teachers already give you, but not now, but later I would recommend you to read a book which is the Real Analysis by Bartley and Serbert, and please read. Yes. Yes, a lot of people do read that book in your level just to crack ISI exam. Okay, so I'm not going into deep into that, but it's there. These are constant time, logarithmic time, everything is explained. Okay. These are actually explanation of how you get to those cases where you are getting what do you call this? These complexities. Okay. Now there is one thing which is called the master theorem. I think I wrote the master theorem. No, I'm not asking you to read real analysis, just that I kept it here. Okay. If you are interested, then only read this part. Otherwise, it's fine. Okay. Let me tell you what is there in the master theorem. Okay. So this is the master theorem, which you will read in your second year of BTech, okay, or second year of engineering. This theorem is kind of the basis for doing complexity analysis. Okay. I just kept it here. Don't worry, not going to go into it. Okay. So we have gone through the performance analysis, all this thing we have already gone through. Comparison plots we have gone through. Okay, a few things that cast performance. Understand that even though I'm saying that all of these will basically n square, n and all this, when you're running it in C, okay, a C programming language or Rust programming language or even Python language, all of these has interpreters and compilers, right? So they are going to do a lot of optimization under the hood, and optimization in the sense of not optimizing for the algorithm, but optimizing for the binary. Okay, so that the binary already has some preloaded data or some preloaded instructions, which will make the running of those algorithms faster. Okay, way faster. And that's why you need to understand that when you run these algorithms, there is an element of uncertainty because on the operating system you are running, because an operating system is a very complex thing that not only optimizes for any of the programs, but it does it under the hood without you even realizing it. So there, like when you compile a code, you can take the binary and basically also generate the assembly code, and from the assembly code you can understand what the heck the compiler did under the hood. Okay, and you will find that the assembly code that is generated for a C code for any of these algorithms will have additional elements added to it. Like, Dutika, do you remember in the last class while we were doing the assembly code, I wrote one assembly code by hand, and when I compared it with the machine code, it was a little bit different. Do you remember that?
Yeah.
Yeah. So that part which I wrote versus the assembly code which was written by the compiler had subtle differences which were there due to the optimization that it does under the hood. Okay. So you need to understand this caching and all this will happen by the compiler, by the interpreter, but you can also yourself implement caching and all these things. Okay. Now there are a few misconceptions which I would like to address. Yeah.
Can we do the rest part in the next class?
It's over actually. Yeah. Okay. It's over. Just a few more things. So common misconceptions are
ডিফারেন্সিয়াল ইকুয়েশন করতে হবে
okay, fine. Just the last few things. Okay. So big O of n log n is always better than n squared. Okay. So you might think that okay, n log n is always better than n squared, but this is not always. For small n square can be faster due to lower constants, and that's what I gave you guys as a homework to compare between n square and n log n. Okay, so understand that if okay, you have your JE, please do the inequality. Okay, now because this is something that is given at interviews at DSA question, and so they will ask you something like which will be better, n log n or n square. So if you say that n log n will always be better than n square, then you are just done. The interview will be like, okay, tata, bye bye. Okay. You are a very good candidate, but probably not for our company. Okay. So understand that there is a particular value depending on the constants. Constants ko baad do. See, take the C as 1. So I want you guys to find out up to which particular input element n square is better than n log n. Quick sort is always n square. No, worst case is n square, but average case is n log n. Built-in sort is always best. Python's time sort hybrid is excellent, but specialized algorithms can be better for specific cases. Then space complexity doesn't matter. In memory constrained environments, O of 1 extra space complexity algorithms are very much crucial. This thing that space complexity doesn't matter, we have a server, we have huge terabytes of storage. No, it's not always the case. Say you are working at a very hardware level environment. Say you are working on a Raspberry Pi where you're constrained by your SD card. So in those cases, the space complexity will matter by a huge margin. That's why I say that if there is a programmer or an engineer who says that space complexity उतना matter नहीं करता भाई, AWS वहां पे रख देंगे, 2-3 थप्पड़ उसको मार देना, ठीक है? That please do your degree again. You are not eligible for your engineering degree. Okay. Now, there are a few advanced topics about the lower bounds and optimality, cache performance, and parallel and distributed sorting. There are algorithms where you can actually do the sorting in multiple processes and thus get a way better time complexity because you're parallelizing the algorithm. But remember, not all algorithms are parallelizable. Okay. So that's one of the important points. And with that, I would like to basically end the class. हाँ हो गया है. This is the end. So if you have questions, you can ask. Probably you guys are too tired to ask any more questions. So it's up to you. I guess no questions. So not only I'm ending the stream. Yeah, I'm ending the stream, but also ending the class here as well. So bye-bye. Good night. Happy Diwali.
আছে